Hello, everyone, and welcome to session 4 of DEM and CFD-DEM with PhasicFlow lecture series. Today, we are going to talk about the CFD-DEM coupling and the basic theory and how we can perform simulations using PhasicFlowPlus. I am Hamidreza Norouzi with my friend and colleague Bahram Haddadi are going to present the details of the CFD-DEM and simulations. Bahram, please say hello and please give us a brief uh, overview of what we have covered up to here.
Okay, hi. Also, hello from my side. Welcome back. As Hamid already mentioned, today we are going to talk about CFD-DEM and CFD-DEM coupling. In the last sessions, we tried to go a bit into detail with what is DEM and how can we do DEM or particle simulations using PhasicFlow. Basically, using just pure DEM and PhasicFlow alone, we can just simulate particles. Also, with that one, you can do quite a lot of different type of simulations and real-life systems. But to extend the possibility further and to be able to simulate even more processes, then usually we need to combine the DEM or the particle flow also with the fluid flow. That's what happens in most of the real processes, and that's where the CFD-DEM or the fluid particle coupling comes into the play. So in today's lecture, Hamid is going to introduce you to the basics of fluid particle coupling, and then we will go through a case setup using the PhasicFlowPlus, which is an extension of PhasicFlow for simulation of for CFD-DEM simulation of particle fluid systems. So basically, PhasicFlowPlus is a coupling between PhasicFlow and OpenFOAM, which we will go into the details through today's session and the next week's session. Today's session will be mostly focused on the unresolved DEM or CFD-DEM simulations, and next week we will focus more on the resolved CFD-DEM simulation. What is resolved and unresolved? Stay tuned and we will find out. So Hamid, the scene is yours. By the way, I will be also here to support Hamid, and when I do it, Hamid is here to support me. If there are any questions, please feel free to put them in the chat. So, and this communication is strongly appreciated because it helps us also to align the talks, to align the teaching, and to see what are your needs, where might be also not clear and where more information is needed. So, Hamid, please.
Thank you very much for your nice introduction. As Bahram said, we are going to talk about fluid particle coupling, and we briefly discuss how resolved and unresolved coupling are different, and when we can apply unresolved coupling and when we can apply resolved coupling. There are three main types of fluid particle coupling, namely one-way coupling, two-way coupling, and four-way coupling. In one-way coupling, we use it when the motion of particles are mainly affected by motion of fluid, while the motion of the particles has no effect or negligible effect on the fluid. This happens when we are dealing with small particle and low concentration or low volume fraction of particles. With small particles, I am thinking about particles in the range of 10 micrometer or less. Two-way coupling is used when we are dealing with larger particle and a little bit higher concentration of the particles. In this coupling method, we have mutual effects of the particles and fluid on each other. It means that particles can affect the fluid flow, and at the same time, fluid can affect the motion of the particles. And in the last one, four-way coupling, we have the full coupling. We call it four-way coupling. It can be applied for larger particles and to the systems with low to high concentration of the particles. In this coupling method, we have mutual effect of the particles and fluid, and also we have particle-particle interactions. This happens especially when we are dealing with higher concentration or higher volume fraction of the particles. With With high concentration of the particle, I mean the volume fraction of the particle higher than 0.01 or something like that, 1%, or even higher. We call the system a concentrated system or a system with high concentration of the particle. And in this system, particle-particle interaction is very probable, and that's why we need to consider this interaction into the modeling. I provided a
Hamid,
kind of... Okay,
maybe a question from my side. So thanks for the nice categorization. So when we are talking about one-way coupling, basically we are looking at the Lagrangian approach. So for the people who are in the CFD field, I think one-way coupling is basically translating to the typical Lagrangian that we are doing in the CFD field. Am I right?
Yes, that's right. That's the term that we use for this type of coupling, Lagrangian coupling, that we can find in, for example, in open form, we can find in Fluent, and of course other CFD softwares.
Yeah, and yeah, the reason for naming it Lagrangian, because basically you're sitting on top of the particle and you're moving with the particle here and there, so that's why it's named like that. And the second question is about the four-way coupling. When we are talking about the four-way coupling, you already mentioned that we have the fluid-particle interaction, particle-fluid interaction, and particle-particle interaction. What's the fourth one? Why do we call it a four-way coupling?
Okay, we have another type of coupling which is somehow three-way coupling, but the fourth one is the effect of the neighboring particle on the fluid-particle interaction between the particle and fluid. Let me just explain it. If we have a single particle in a system, in a fluid, we have the pure effect of the fluid on the particle. But if we consider the same system, but we put other particles around that particle, not only we have particle-particle interactions, which is the result of the mechanical interaction between the particles, we also have the effect of the surrounding particle on the fluid-particle interaction. This is the third effect that I have not mentioned it here, but yeah, you're right. The third one is that effect.
Okay, thank you very much. So basically, when we are talking about higher order coupling, so it's better to go for a four-way rather than a three-way, because we already have the information. Why not use it? And I think computationally they are quite similar. So that's why we categorize them in one and two-way. In one and two-way, the computational effort is rather low. In four-way, the computational effort is much higher. But yeah, then you get also quite lots of information out of these. But the good news is that using the PhasicFlow and PhasicFlowPlus, this coupling or this effort should be brought to a minimum. So using this very efficient usage of the hardware and the structure of the code should help us to do also four-way coupling simulations quite efficiently.
Yes, exactly. Yeah, and this is the map that I call it coupling map, and it has two axes. The horizontal axis is Stokes number, and the vertical axis is the solid volume fraction. So when we are going to decide which type of coupling is suitable for our system, we should think about the volume fraction of the particles, average volume fraction of the particles, and at the same time, we should think about the Stokes number. Stokes number is the ratio of the particle characteristic time over fluid characteristics time. I prepared this map for air, since the typical fluid for example, gas fluidization or gas solid flow system is usually air, but we can apply the same analysis for other fluids rather than air. And I translated the Stokes number to the particle diameter when the time characteristics of the fluid is 0.5. As you see, the Stokes number varies from very low values to very high values, and this is translated into a system with very low particle size to very large particle size. As we see here, 1 micrometer to 100 millimeters. So this is a wide span of the particle size. When the particle size is small, of course, the Stokes number is low. It means that particles have negligible effect on the fluid, and we can do somehow one-way coupling. But as the concentration of the particles increase in the system, then one-way coupling somehow deviates from its assumption model assumptions, and the two-way coupling comes into play, and we should apply the two-way coupling. And then still at very low particle sizes, we don't need to consider the four-way coupling for the system. Of course, we can do that, but the cost of the calculation cost is very high, and if it is possible for us, we should go for two-way or one-way coupling in the system if it is really possible. But when we are going from the left to the right-hand side, the size of the particle increases, and in this system, particles start affecting the fluid flow in the system. And then this is the time that two-way coupling and four-way coupling come into the play. The only difference between two-way coupling and four-way coupling is that when I'm thinking about the situation that particles affect the fluid flow, then the next question is that what is the concentration or the volume fraction of the particles? If the volume fraction of the particles is low, as you see in the green area, then two-way coupling is a right choice. But when the concentration increases, the solid volume fraction increases, then we should go to the four-way coupling. And if we continue to increase the size of the particle to systems like a few millimeters or tens of millimeters, then somehow we are in a situation where fluid does not affect the particles' motion. It means that the system is kind of fixed bed simulation or fixed bed system, and particles only affect the fluid motion. So as you see here, for large particle sizes, and of course for the fixed bed, we are in the range of the in the area of high solid volume fraction, we have fixed bed. So as you see here, we are in this map, we have a system with negligible effect of the particles, and fluid affect the fluid particles motion. And from this area to this area, a transition occurs, and we end up in a system where particles only affect the fluid motion, and fluid motion has no effect on the particles. So this is the coupling map, and this map helps us to choose the right way and the right coupling strategy for our simulation. And of course, we can do all the simulations with the four-way coupling. If it is done correctly, it can predict the behavior of the fixed bed. It can predict the behavior of a two-way coupling system or one-way coupling system, but at a very high computational time and computational cost. In PhasicFlow, we perform fluid particle coupling with four-way approach. For four-way approach, we have two types of the coupling. We have resolved CFD-DEM and we have unresolved CFD-DEM. When the size of the fluid cells is much, much smaller than the size of the particles, we are in unresolved CFD-DEM. In this kind of coupling, we are solving the fluid flow around the particles.
Okay, Hamid, I'm not sure if it's from my side, but I lost your sound for a few seconds. Hamid? Okay, so it seems that Hamid sound has some troubles when it's disconnected, but then I just try to complete it here. Basically, in a four-way CFD-DEM coupling, we have two possibilities: going for a resolved approach or an unresolved approach. In a resolved approach, the particle is big enough that that it covers a few cells. So I think Hamid is back, but Hamid, I'm just trying to repeat the last slide that you already had. So.
Okay, should I start from the beginning of the this slide or just continue?
Just simply leave it. I will go on. I will try to finish this slide because I try to re-explain it. So basically, in the resolved approach, the particles are bigger than the computational cells. So then we resolve the fluid flow around the particles. So we can form the boundary layers, and we can see the quite detailed information of or the effect or interaction between the particle and the fluid. In the second approach, basically the particles are much smaller than the computational cell, so therefore we don't resolve any flow details around each and every particle. We just use an average flow field information, or like the pressure, velocity, temperature, or whatever that we need to calculate the properties on the particle, like the drag force, like the heat transfer, and so forth and so on. So that's the main difference between the resolved and unresolved. Hamid.
Okay, thank you. And thank you very much for your explanation. Yeah, that's right. And let me just add one point to the unresolved CFD-DEM. The point here is that when we are dealing with this system, we need to calculate new variables that represent the dispersed phase. These new variables are solid volume fraction or volume fraction of the particles, and also the average momentum transfer between or momentum exchange between the solid phase and the fluid phase. And this is the essence of the unresolved CFD-DEM, and we are going to talk about it in more details. In this session, we are going to cover the unresolved CFD-DEM, and in the next session, we are going to cover the resolved CFD-DEM. In the unresolved CFD-DEM, the equations for the fluid phase are continuity and momentum equations. As you see here, we are considering the effect of the volume fraction of the particles. Of course, the volume fraction of the fluid, which is somehow 1 minus volume fraction of the particles. And also, we are also considering the effect of the momentum exchange between the fluid phase and particle phase. This formula is used to calculate the momentum exchange or momentum source term in the momentum equation. And as you see here, we are taking into account the drag force, the unsteady state force, and lift force. In many situations, we may want to ignore the effect of unsteady state and lift force and only consider the drag force, especially when we are dealing with the gas solid flows where there are no large or there are no gradient in the fluid phase, then the unsteady state force or the lift force is negligible. The equations for the particle phase is similar to what we have in the DEM. The addition here is the fluid particle force, which is considered in the Newton's second law of motion. And this fluid particle interaction force consists of drag force on a steady state force, pressure gradient force or buoyant force, and again the stress tensor force and lift force. And again, when we are dealing, for example, with a system like fluidized bed, we only consider the drag force and the pressure gradient force, and the other three terms are negligible. Here, as I told you, there are two important parameters that we should calculate during the coupling. The first one is the volume fraction of the fluid, and the second one is the source term of the momentum exchange. The equation that is used here is a weighted equation that is performed on the particles in the system. As you see here, we are performing a summation over the particles in the list of the particle list of the cell, and this summation is weighted by a lambda. And this lambda is evaluated by different methods that we call them mapping methods. The same also happens here when we are calculating the momentum exchange term. We use the same summation, and the summation is performed over the particles on the particle list of each cell, and the same weighting factor is used here. This weighting factor is determined by a method that is called mapping method. The first one is the PCM, or particle centroid method. It means that in this method, when we are mapping the particle properties on each fluid cell, we only consider the center of the particle. If the center of the particle is inside one cell, then the whole property of that particle is assigned to that cell, like the figure that you see here. If we are, for example, calculating the porosity of the particles in this cell that we are showing here, then since the center of the particles is inside this cell, then we assume that the whole volume of the particle is inside this cell. And the same also goes for the momentum transfer term. The other method is called divided volume 29. This method divides the whole particle into 29 equal volumes, and each of these subvolumes has its own center. And based on the location of the center of each subvolume, we assign that portion of the property to the cells. For example, as you see here, we are assigning a portion of the volume to this cell because we have a number of the subvolumes inside this cell, and this we also assigning another portion of the particle property to this cell, and this cell. So as we compare these two methods, we see that the accuracy of the particle properties mapping onto the cells is much higher than in the divided volume 29 when we are comparing it to PCM method. The other method is to use a kind of statistical or Gaussian kernel method. In this way, or in this method, we assume a kind of statistical kernel that distributes the particle properties over the cells, and the weighting factor decreases as we go further away from the particle center. As you see here, the effect of the particle near the particle center is much higher compared to the effect of the particle when we are away from the particle center. So in this way, as you see, we are smoothly distributing the particle properties over the cells. So using Gaussian kernel creates a smoothen property over the cells, and this somehow prevents the simulation from sudden changes in the particle properties when we are mapping particle properties over fluid cells. These are the three main approaches for mapping particle properties over fluid cells, and we have implemented these methods in PhasicFlow. The first method is self, or it's the same, PCM, similar to PCM. We call it self in PhasicFlow. And this is used when the cell-to-particle size ratio is large, typically larger than 6. The second method is subdivision 29 or 29. It is only used for calculating the porosity. And we use it when the cell-to-particle size ratio is larger than 3. The Gaussian method is there to have the complete list, but honestly, we do not use it because we have the better approaches to use when we are dealing with the statistical method. The next method is adaptive Gaussian. In my opinion, this is the best method to map the particles properties over fluid cells. It has only one drawback. It can be used for orthogonal mesh, and when the non-orthogonality of the mesh increases, then the accuracy of this method reduces. The other method, which is categorized as the statistical kernel method, is Gaussian integral. It is somehow similar to adaptive Gaussian, but the error for calculating or mapping particle properties over cell is a bit higher than the adaptive Gaussian. That's why I say that adaptive Gaussian is the best choice for us when we are going to use the Gaussian kernel methods. The last one is the diffusion method. It somehow uses a diffusion equation and diffuses the properties over the cells, somehow similar to adaptive Gaussian, but it does, or it makes it performs the a smoothing operation using the diffusion equation. It can be used for orthogonal meshes, but I think that the strength of the diffusion method is where we are going to use it for non-orthogonal meshes. Otherwise, when we are dealing with the orthogonal mesh, I think that the adaptive Gaussian and Gaussian integral are the best choices. And again, for the diffusion method, we need to provide a parameter that is called a standard deviation, and the standard deviation should be between 3 to 6 times the particle diameter. These are the mapping method, and of course, Bahram will talk about the mapping method when he's doing the simulation and how you can select different mapping method in PhasicFlow. The last topic that I'm going to talk about is the calculation sequence in the CFD-DEM. As you see here, the first step is to initialize the parameters for the CFD and DEM and coupling parts. And we have three main parts, or three main steps in the calculations. The first step is to calculate the coupling properties, like calculate having the particle position, particle velocities, fluid velocities, and cell structure, mesh structure. We can calculate the porosity of the particles in each cell. We can calculate the momentum exchange term and drag force and fluid particle force on each particle. Having these values, we can perform DEM calculations and CFD calculations. Since typically the delta T for DEM calculation is smaller than the delta T of the CFD, we perform DEM iteration m times. M is the ratio of the delta T of the fluid over delta T of the particles. And after that, we perform the calculations of the CFD, and the result of these two steps of the calculations are velocity of particles, position of particles, pressure in the fluid side, and velocity in the fluid side. And then we go to the next time step, and this iteration or this loop continues until the end of the simulation time. This is the overview of the calculations that we perform in the CFD-DEM, and of course we perform in the PhasicFlow Plus. I think I covered the most important parts, but we missed too much details. And if you are going to learn more about the coupling, I again refer you to the coupling book that I introduced to you in the previous sessions. Okay, Bahram, do you have any questions?
Yeah, I know, but there is a question in the chat. So just wanted to know if it's possible to simulate flocculants, a fluid mixture, oil and water emulsified, and introduction of flocculants to help the mixture get separated. Would DEM be helpful here?
Okay. If the system is only two liquids, then we do not call it the DEM system. We call it the discrete bubble or discrete droplet system. Yeah, it's possible, and we can use the same approach that we use in DEM to somehow simulate and model the motion of the droplets in that system. And of course, since we are tracking the individual droplets in the system, the accuracy of the simulation also increases. But in the context of this PhasicFlow, no, because we do not consider discrete bubbles, at least at the moment, or discrete droplets.
Great. Thank you very much.
Okay.
Okay, good. I think now it's time to go to a bit practical stuff and showing to you the PhasicFlowPlus. So the first thing that I want to show you is PhasicFlowPlus. Is how to install the PhasicFlowPlus. Basically, the installation of PhasicFlowPlus is quite straightforward. The same. I will share my screen. Yep. I hope that you can see my screen.
Yes.
Okay, great. Thank you very much. So the installation of PhasicFlowPlus is basically quite straightforward, the same as PhasicFlow. But as prerequisites, so for PhasicFlow, you remember the main prerequisite was installation of Focus as the polarization backend. For the PhasicFlowPlus, we have two prerequisites. One is, of course, PhasicFlow, and the second one is OpenFOAM, because PhasicFlowPlus, at least at the current state, is the coupling between OpenFOAM and PhasicFlow. So please make sure that you have these two packages installed. But how can you do it? So let's go to the PhasicFlowPlus webpage, and then we will find out. So there is a bit explanation, and then comes this point, how to build PhasicFlowPlus. So version 1 and version 0.1. Version 0.1 is the released version currently. It's compatible with OpenFOAM 9 and with the PhasicFlow version 0.1. Yeah, although this is the released version, but I recommend you to go for the version 1, so 1.0, which we are going to release hopefully in soon future, which is a coupling between PhasicFlow version 1, that we have much more functionality built into it, and OpenFOAM version 24.
Okay, Bahram, please, sorry for interruption, but the font size is very small. May you enlarge the font?
Yes. Yes, sure.
Yeah, that's better now.
Good. Basically, the installation is quite easy and straightforward. So you just go to your PhasicFlow installation folder, then you download the PhasicFlowPlus from its GitHub page, and then you go in there and try to make it. Wait, I just want to go to the installation page. Here. Oh, okay, I cannot really find it here. Basically, there are three possibilities. So there are three possibilities for installing and compiling PhasicFlow. If you go, yeah, it's here now. I remember it. Yeah. If you go to the install PhasicFlow, you have the three possibilities. You can install PhasicFlow either in serial mode or in CPU parallelized or GPU parallelized. So, and based on the compilation and installation that you have there, the DEM part will be also done the same way at this side. So if you have your PhasicFlow, for example, compiled on the CPU parallelization, then also PhasicFlowPlus will be parallelized on the CPU, also on the DEM side. On the CFD side, it's all the time, at least on the current status, parallelized on the CPU. So we are using MPI parallelization for the CFD side. So the installation is quite easy. Go to your PhasicFlow installation directory. In this case, or in most of the cases, it's your home directory. Download the PhasicFlowPlus from the official repository from the GitHub, and then simply unpack it, go to the PhasicFlowPlus directory, and run the command all-wmake. And that's basically all you need to do to have the PhasicFlowPlus compiled on your system. So to show it to you, how does it look like?
I have a question here before you start doing that. Is it? It says that it's compatible with OpenFOAM version 24. Is it also compatible with latest version of OpenFOAM? Have you any experience with that?
Honestly speaking, I've not compiled it on 20 because I think the latest version from ESI. So for those of you, which I hope that you all are familiar with OpenFOAM, you know that there are three main branches, and we are working on the ESI branch. So at least for the new release of the PhasicFlowPlus. Honestly speaking, I have not tested on 2506, which is the latest release from ESI. We just tested on 2406, and for that one, the compatibility is confirmed. We are sure it's working, so we have tested it. For the others, most probably it will work. But honestly speaking, I've not tried it. And even if it does not work, it needs just very small modifications till it gets compatible.
Okay, thank you.
You're welcome. With OpenFOAM, with the OpenFOAM.com or with the community version, you will have a bit more fun to make it compatible. But still, it's not too much effort, but yeah, it's a bit effort to make it also compatible with the community version. But the version that we are supporting, at least at the moment, is the ESI release. And the main reason behind that is that the solver structure in the ESI release is a bit easier to be further developed. So that's the main reason that we decided to go for the ESI branch of OpenFOAM. Good. So as you can see, if I go to my home, to the PhasicFlow folder, I have my PhasicFlow installation, which is PhasicFlow version 1. And then as soon as you download and you unpack the PhasicFlowPlus, then you get a folder which is called PhasicFlow coupling. If you follow the instruction which is given on the PhasicFlowPlus GitHub page. If I go to the PhasicFlow coupling, then there are a few files and folders, which among them, for especially today's and next week's lecture, these tutorials plays the most important role. But before going to these tutorials, which as you could already guess, we can find the tutorial cases for running the CFD-DEM coupling solvers. We will have a look into the solvers folder, which should give us an idea which solvers are available in PhasicFlowPlus. We have a group of solvers which we call the legacy. So basically, these are the older versions of developments that we have. We still kept them. We might drop them as soon as we release the version 1.0, but they are there for the moment as a reference. But the more important and interesting things are sitting out here. So particle track PF Plus, if you go there, there is nothing there because this solver is under development. Again, I repeat it once more, this is not the released version. That's why there are things which are still incomplete, which will get hopefully complete by the time of release. But the other solvers, like the Resolved Sphere PF Plus, Resolved Sphere VOF PF Plus, are the resolved solvers for CFD-DEM coupling, which we are going to discuss them and go through them in more detail in the next session. But the two ones which are more interesting for today's lecture are the Unresolved Grain PF Plus and Unresolved Sphere PF Plus. As you could already guess, the Sphere PF Plus is the pure unresolved CFD-DEM coupling solver with non-coarse grain approach. And if you want to use the coarse graining, yeah, the good news is that we also have the coarse graining on the CFD-DEM coupling. Then you can go for this unresolved grain PF+. I'm not going to talk about this one today because this case setup is quite similar to the other one. We will go through the sphere PF+. And if you want to know about the details of coarse graining, please revisit the lecture from last time. Hamid did a very nice job there with explaining the details and how it works and how can you set it up. So looking into the unresolved sphere PF+, there are two folders, version 9 and version 24. So version 9 is still the older version, which again, most probably we are going to drop it by the release, but we have it there for the moment for the further developments of the other part. And version 24 is the actual version which we are working on. So if you go into the version 24, for those of you who are familiar with also OpenFOAM source code, we have a typical OpenFOAM solver structure, a C file and a few header files, which are hosting our velocity equation, pressure equation, and the fields that we are creating. Let's start with the C file, because the main magic is happening in the C file. So going to the C file, we have the typical headers. So, and the licensing for both OpenFOAM and PhasicFlow and PhasicFlowPlus, of course. And then the magic starts from here, where we have the OpenFOAM. These are the header files that we need for OpenFOAM. I don't really go to the details here for the source code because this is not a session for programming in PhasicFlowPlus, but I just want to show to you how the code looks like and somehow visualize what Hamid already showed in his presentation in the source code. So these are the header files that are the functionalities that we need to make the CFD side running. And this is the header file that we need for the DEM side to be engaged in the simulation. Then continuing down here, we will start with the main function in the C file. So that's a typical approach in the C and C++ programming. Then the first header files to create the time, to create the mesh, and to initialize the settings on the CFD side. Then, in the next part, we activate the parallelization, basically. And then we start creating the fields. And that's this file. Looking into the create fields file, if I go up here, basically we are creating the pressure field. We are creating the velocity field. I don't repeat I repeat it again. We don't go to the details here. If you are interested into OpenFOAM programming, which also to a good extent also cover the programming in PhasicFlowPlus, I would recommend that you visit our other lecture series, which is on OpenFOAM programming. And in there, we try to go a bit into details regarding these pieces of code or snippets of code. Good. Here we create the object from the coupling, or which basically engage the DEM part and the coupling section of the code. And then, yeah, we create the flux field. Then we try to set the references for the pressure field. These are typical OpenFOAM code. And then we, of course, we create the viscosity model or transport model. We also create and activate the turbulence model. Then we create the density field. And from there, we also create the phase velocity field. So these are the typical fields that we need in a CFD calculation, except for this part, which are the object or the parts that we need for DEM and CFD-DEM coupling calculations. So we create the fields in here, then we basically validate the turbulence, we do all the time settings, and we start the time loop. By starting the time loop, yes, please.
We didn't have your voice for around 30 seconds. May you please repeat the last sentences?
Yes, sure. Basically, I will continue here. In the create fields, we created all the necessary fields for running CFD and, of course, CFD-DEM calculations. We also created the object for calling in the DEM, or basically simply PhasicFlow. And then We validated the turbulence model, so we calculated the Courant number, we set the time settings, and we started our time settings. Again, I'm really going through this stuff very fast because it's not the focus for today. I just want to show you what Hamid already explained. Where does it show itself in the source code? Maybe
Up to
in future
here,
we also
we just initialize the CFD and DEM parameters. Am I right?
Yes, in a simple language and in a single sentence, that was the summary of what I already mentioned. So maybe in sometime in future, we also do a lecture on programming in PhasicFlow and PhasicFlowPlus, but that's not fixed yet. So then when we go into the time loop, basically the typical calculations for time stepping and everything, and then in here we start the timers. What we also do in the PhasicFlow and PhasicFlowPlus, we calculate how much time do we spend in different sections of the code. This is a quite nice piece of information which can help you to optimize the code and running the simulations. Then we enter the pimple loop. So, and in pimple loop, of course, putting the CFD timers on the pause, because this is the part, this is the first part that we are doing the DEM calculations. We do this DEM calculation once per pimple loop because we don't need it more, and this is an explicit coupling. If you recall the flowchart that Hamid showed, we calculate we have the DEM and the CFD, or we have the particle and fluid field and properties. Based on this, we calculate the interactions. So, but this information comes from the previous time step. So therefore, this is sort of an explicit coupling between the CFD and DEM, or the fluid and the particles. So we get the information from the DEM side. We try to calculate the porosity field. Then we try to calculate the fluid interaction, and we pass this information to DEM for updating the DEM. And in the next line, basically, we do the DEM iteration and we update our DEM. And then we start the CFD timers again, because from here onwards, we are going into the CFD calculations. So the updating for the changing mesh, this is typical OpenFOAM stuff. And then the next part of the magic is happening in the U and P equation. If I go to the U equation, basically, you already remembered, Hamid showed that we are bringing the porosity into the U equation. That's where the porosity is called from this coupling object that we created, and it's pushed into the equations. And of course, down here. And the same is also happening in the pressure correction equation. So if you look at here, we are pushing the porosity to the pressure equations. Good. So this was a very fast and brief look into the source code, that you can see the equations that Hamid already showed on the paper. How does it appear in the source code? But let's go to the more interesting and more relevant part for today, and that's sitting in the tutorials folder. So again, for each and every solver that we have in PhasicFlow and PhasicFlowPlus, we try to provide at least one tutorial and one case how to set up a simulation with that one. So for today's section, we are looking into the unresolved sphere PF+, and if you look into this folder, there are 3 tutorials already provided. The tutorial that we are going to cover for today is fluidized bed, and it's a cylindrical fluidized bed. Basically, we have 2. This fluidized bed alone is a rectangular fluidized bed, and we have a second one which is a cylindrical fluidized bed. So that's the one that we want to go through for today, but basically all 3 cases have very similar settings. As usual, we copy this tutorial to our working directory. In this case, it will be my desktop. As you can see, I have it also second time on my desktop because I executed prior to the lecture, because it takes a bit time till we finish it. I just did it that we have it ready for the post-processing also.
Okay, I have a question here. How long does it take?
Yes.
Did it take?
Basically, the PhasicFlow compilation that I have on my PC is a GPU one, and with the GPU compilation, I also have an A4000 GPU card. With that GPU card and with the GPU case setup, it took around 1 hour and 20 minutes for 10 seconds of simulation and 50,000 particles. But we will see these details also in the simulation. Yeah, thank you. That's a very good question. Now I can maybe take a step back. If you run it in serial mode for the DEM, definitely it will take the longest. If you run it on the CPU, it takes probably longer than the GPU, but the GPU is usually the fastest one. The main limitation with the GPU execution is the number of particles. But since in this case, I'm looking at the 50,000 particles, that should be quite fine. With my GPU, I can run up to a few million particles. Yes, Hamid.
Before you start talking about the simulation case setup, we have two questions here. The first question is, what limitation do we have in terms of particle numbers to couple with the fluid model?
Basically, the limitation comes from the hardware side. So as I already mentioned, if you are doing GPU calculations, it basically in both cases, it depends on the amount of RAM that you have available or memory that you have available. If you're doing the calculations on the GPU side, the limitation is the GPU memory. And so as I said, for my card, it's an A4000. I'm not really sure about the amount of RAM I have in there.
Gigabytes,
I think it's I think it's a 16 one, yes. With this one, I can go up to a few million particles. So
around 16 millions. 16 millions.
Great. Thank you very much. So for this very nice scalability information. And but if I go for the CPU, again, it depends on the amount of RAM that you have on your system. So I would say for around 32 gigabytes, we should, or 16 gigabytes, we should expect the same number of particles there. But the computations will be much, much slower. It will take quite some time to do the computations.
And do you have any experience in the CFD-DEM simulations? What was the highest number of the particles that you performed simulation with?
Basically, the highest number of particles that we did was on an A100 GPU card with 40 or I think it was 40 gigabytes of memory, and that was around 18 million particles. But there is also another piece of news. What we are also working on is parallelization on multi-GPU cards. As soon as that part of the code is also available, then if we have two cards with 16 gigabytes of memory, then we can go for double the amount of particles.
Exactly. And the other question is how to determine the DEM and CFD time step. This is a very critical question.
Basically, for the DEM, I leave it to Hamid, but I will answer the CFD part. When we are looking at the CFD time stepping, you look at the typical Courant number. So you look into the Courant number and you try to keep your Courant number below 1. That's the typical suggestion. For DEM, I think Hamid is the better reference.
Yeah, that for the CFD, you're absolutely right. And for the DEM, of course, we covered it in the previous sessions. We go for the critical time step, we calculate it, and then we select a right resolution for the time step. And based on the resolution that we require for the time step, we select the time step, and that's all for DEM. But for the coupling, when we are dealing with the coupling, a very important parameter here is the time scale of the particles in the system. When the time scale of the particles is very low, we need to resolve that motion. So somehow, not only the CFD side is important, and also the DEM side is important. If the coupling time scale is lower than the CFD and DEM, we should choose the coupling side time scale or coupling side delta T. So this is the other important factor we should consider when we are dealing with a system in which the motion of the particles is changing very rapidly. Then we should choose the small enough time step for the simulation to resolve the rapid motion of the particles due to the fluid effects. So this is something that we should consider.
Yeah, thank you very much. That was also a very good point. Basically, in the classical Courant number, we are looking at the fluid velocity. But if Hamid is definitely right, if we have fluid and particles, then particles also play, or particle velocity plays an important role also there.
Yeah.
Good.
And we have another question. Sorry, because I want to finish the questions, and after
Please
that
go
you
on.
can go. Yeah. How about Unresolved VOF-DEM? Is it going to be added in future?
Yes, we don't have a fixed deadline and time plan for that, but most probably yes. So whatever solvers that we can think of and we think might be of general interest and use, we will definitely consider them. So that can be definitely also a possibility. And but what we also strongly appreciate and encourage from our side, if you can do it and if you have the background and knowledge for doing it, then you're also very welcome to do it, and we of course take it into the PhasicFlowPlus. But yeah, the short answer is that yes, we try to consider as many scenarios and as many solvers as possible, but it will take time till we manage to introduce them.
And of course, in the process of your development, we are there to support you with additional help, and maybe we can give you some guidance on the development side.
Thank you very much. Yeah, that's also an offer that can come from or that comes from our side. Please feel free to use it. Good. If we go into the case setup, there are a few folders and a few files. So let me start with the files that we can kick them out from the very beginning. There is a README file. Basically, this README is the file that explains the case, the simulation case setup and different settings in there. And it's in MD format because this is the format that can be read in by the GitHub. So when you open this case in the GitHub, then you see this README in a very nice format, including this picture in there, and you can go through it and you can follow it. So basically, these two are not really that relevant for today. Then we have the all-run file. The all-run file for me is usually the help file for how to run, how to set this case up and how to run it. What are the pre-processing and post-processing steps for running the simulation? And I will open it here because we will look at it in a later stage. First, I will explain about the folders which are available here. So you already got introduced to the PhasicFlow, so therefore you should know the case setup and the settings folder. These are the two folders that we need to do the setup for the DM, for the particle side, or simply to say for the PhasicFlow. We will go through them one by one. Then we have the two other folders, which is the constant and the system and fluid field. Basically, constant and system are the typical OpenFOAM folders, so that you find the fluid settings in there. For your information, the coupling setting is also sitting inside the constant folder. So, but we will go through it anyways in a few seconds. And then we have also the fluid field. These are the backup files that we use for starting the CFD and the CFD-DEM simulation. As you already know, in the CFD or in the OpenFOAM simulation, we usually have an initial folder, which is usually 0. But in here, we don't have it. We're going to create it in a later stage, and you will see why and how it works. Good. Before I go into the all-run file, let's look into these folders and see what do we have in there. If I go into the case setup folder, we have the two files, interaction and shapes. They are the very typical PhasicFlow files. In the interaction, basically we define the type of materials that we have on the particle side. On the DEM side, we have the sphere material and we have the wall material. Then we define their densities. Then we also define the interaction model and the interaction parameters for the particles and walls. And we also define the type of contact search which is used on the DEM side. So as you can see, this is a pure DEM setting. For more detail, please go back to the previous sessions. That's also true for the shapes file. In the shapes, we can see the name of the particles or the name that we assign to the particles, the diameter of the particles. As you can see in here, we are going for a mono-sized particles in this simulation, and we are assigning the sphere material as the material property to these particles. So nothing specific in here, or nothing new, better to say, in here. There's definitely specific stuff in here. Then going back, let's go to the settings, which is again the DEM part of the story. If I open the files in here, we have the domain tick where we define the global box, which defines our DEM domain. And if the particles are going outside this domain, this is what happens to them. Basically, they get exited or removed from the simulation. As simple as that. We have the geometry dict. In the geometry dict, we are bringing in, so that's also a new functionality. I don't recall it if Hamid explained it last time, but we have the possibility to import the geometry from the CFD side. So this, in the geometry dict, Hamid explained it last time, we can define a geometry. We can create a geometry using by importing an STL, but there is a third possibility that we're going to talk about it today, and that's importing the geometry using an existing CFD mesh. If we have a CFD mesh, we can import it in like this. Basically, we take the patches from the CFD side, we can take each and every boundary from the CFD side, and then we import it into the DEM side. So first we say, okay, what type is it? The type is foam patch wall. So that's the type that we have on the CFD. We have on the CFD mesh side. We call it inlet. That's the name that you're going to give it to it on the DEM side, and we are going to assign it the material property of material wall or wall material. So that's what we already defined in an earlier stage. We do it for all the boundaries, inlet, outlet, and the cylinder, the third boundary that exists in there. For that one, of course, we need the CFD mesh. So therefore, we need to create the CFD mesh prior to create the geometry on the DEM side. But that's something that we will see in this all-run script. Then going to the particles dig, basically the classical PhasicFlow setup. So these are the initial settings of the particles, or these are the initial settings that we apply to each particle regarding the linear velocity, the rotational velocity, and the type of the particle. And then we start positioning the particles. So in this case, we are positioning the particles randomly. We are positioning 50,000 particles with the distance of 2 millimeters, which is the minimum distance, because this was the diameter of each and every particle. And we try to locate them in 50 iterations. We are locating them in a cylinder with the following coordinates. I think you could already guess these coordinates is somehow the same as our CFD or our CFD mesh coordinates for positioning the particles. And the next part is the settings dig. In the setting dig, basically, Hamid did a very great job last time. He explained everything, but there are 4 parameters which are relevant for today, and that's the start time, end time, save interval, and time precision. Since we are talking about the coupling, these 4 parameters need to be synchronized between CFD and DEM. So therefore, CFD is the master in this case. So these parameters are read from the CFD time. So it's from the CFD side. So they are read from the control dict of OpenFOAM into this simulation also. So basically, it starts the simulation from there. It ends the simulation from the end time, which is defined there. And also the save interval and time precision are read from this control dict. In this simulation for today, we have 2 steps. In the first step, we are doing a pure DEM simulation. We are positioning the particles. We are letting the particles using a DEM simulation to fall down and to settle. And then from there, we start the simulation. So therefore, these are also relevant for today's simulation. Basically, for the DEM simulation, we run it from the time 0 to time 0.25 seconds to let the particles to settle. Then we save them every 0.5 seconds with a time precision of 4. And then for the CFD simulation, that's what we will see shortly, we will start from time 0.25.
Can you show the control dict here at the same time?
Yes, that's a good idea, and that makes sense. Going to control dict here, so you can see the start time for the CFD, which is basically the start time for the CFD-DEM coupling, is from 0.25. And from 0.25 onwards, the start time, the end time, and also the precision will be mastered or will be controlled by the CFD side or by the OpenFOAM side.
And what about the delta T?
So the delta T, that's what you already explained earlier. So the CFD delta T will be read from here, will be calculated from this, or if you have it on the modifiable, it will be calculated based on the Courant number. Sorry, if you have a, what's the name? If you have a adjustable time
Adjust.
step, then it calculates based on the current number, or if you have it as a fixed, then it looks at this number. And for the DEM, it reads it from the settings dict of the DEM. So this is the delta T which will be used on the DEM side. Good. Now let's have a look into the constant folder. So in the constant folder, we have 3 files. The first file is coupling properties. In the coupling property, basically, we are defining the coupling settings. Let's start from up here. So the first setting, Hamid already did a great job. Then he explained about the distribution methods that we have in the coupling. So we have this PCM, particle cell method, then we have the subdivision 29, then we have cell distribution. So you can see all these options in here. For example, for the cell distribution, in this case, we selected the Gaussian integral, which basically uses a kernel method to distribute or to distribute the porosity based on this kernel method into the neighboring cells, into the central cell and the neighboring cells. So we use this, and then for the porosity calculation, we use the cell distribution. Of course, we can use the PCM, we can use subdivision 29, and also for the cell distribution, sorry that I mixed between the 2 languages for a second.
Yeah, this happens.
Yeah,
it also happens to me.
Yeah, because whenever I read it for myself, I call it in both languages, so sorry for that. When they are using the cell distribution, we can also select different options like the self, like the Gaussian, like adaptive Gaussian, and of course Gaussian integral and diffusion in there. Then the next thing that we need to define, especially when we're talking about an unresolved approach, is the calculation of the drag force on the particle. Hamid already explained it. So in this case, we can use different options, but for this simulation, we are going for the defleature, which is a quite known one and is a quite nicely developed one. For calculation of the fluid velocity, we can use either cell. So basically, when we are calculating the fluid velocity at the location of a particle, we can go for 2 approaches. We can go for either cell or particle. In the cell approach, we are using the value from cell center, and we assign it for the drag calculation on the particle. Or we can go for a particle, which is an interpolation approach. Basically, we interpolate the velocity to the location of the particle. This is more accurate, but of course, computationally more expensive. The same also applies for the solid or for the particle velocity. And yeah, these are the settings that we have on the coupling side. Then also there is the residual Reynolds number. So whenever we need to calculate the Reynolds number, this is the minimum value. So if the Reynolds number which gets calculated, for example, for calculation of the drag value using the defleature approach, if the drag is smaller than this, or is Reynolds is smaller than this, then this value will be taken in. The main reason is that we don't end up by division by 0. So you can, of course, use smaller numbers. And this is the particle mapping, which basically we also had on the PhasicFlow and on the DEM calculations. The main recommendation that I can give in here for the domain update interval, if the what's the name, are getting smaller.
Particles.
Yes, sorry. Thank you for that. If the particles are getting smaller, then go for a smaller value. But as a general recommendation, this value of 0.01 works for most of the case setups that we had. Good. That was the constant. Then looking into the system, we have the block mesh, which is the file for creation of the CFD mesh. And we have the decompose partict, which is for running the CFD side in the parallel mode, and FE schemes and FE solution for defining the schemes and the solution approaches on the CFD side. So these are typical OpenFOAM case setups that basically, if you also look into them, they are quite typical CFD or OpenFOAM settings. There is nothing specific or special in here. And that's also true for FE solution. Good. Then we have this fluid field. This fluid field also includes our CFD case setup or CFD initialization files. Then the pressure and velocity files are as usual. The only new file in here is the alpha, which is basically standing for the phase fraction. But if
Is
you
it
look into the
phase
alpha,
fraction of the fluid or phase fraction of the solid?
as far as I remember, it was phase fraction of the solid.
Oh.
Am I right? Please correct me if I'm wrong.
I guess it is the phase fraction of the fluid.
Okay, then. But for that, we can also look into the source code.
Yeah.
Let's have a look. Yeah. Yeah. No, I would say it's easier if you look here. Yes, you're right. That's a phase fraction of the fluid. If that gets multiplied by U, that's a phase fraction of fluid. That's why once in a while also looking into the source code.
And the fun part here is that you wrote this part of the code, the solver, but you forgot.
Yes.
Somehow.
That's one of my weak points. I forget the things too fast, but that's also the good point that we have the things documented in the source code. Good. So that was the alpha. So that's the phase fraction of fluid, and we just need to define some initial values, and it gets updated during the simulations. Now let's look into the very first file that I opened, and that was, where is it? It's all run file. So to run the simulation, as I said, this is for me usually the health file. We have the block mesh, which creates the CFD mesh. Let's run it. So for running the coupling, of course, you have to have both PhasicFlow and PhasicFlow 1 and OpenFOAM 2406 active. So that's what I already have them activated because I already added them to my personal Bash RC file. So then let's run it.
What is the configuration? Okay, after this one, what is the configuration of the DEM side? Is it a CUDA or OpenMP or serial? Which one is it?
In my case, it's a CUDA. It's a micro case. It's a CUDA compilation, but depending on your system, you might have different ones. But we will see it. I will also try to show it to you in the log file. So I created the CFD mesh. If I go back to my constant folder, now there is a folder polymesh, so the CFD mesh is sitting there. And the next step, let's create the particles. We can create either the geometry or particles, but let's start with the particles. Now we created and we positioned the 50,000 particles. You can see they are positioned. Let's create the geometry. So now we created, or basically we imported the geometry from CFD to the DEM side. And now we can run the DEM simulation. So sphere ground flow. And if I start running that, let me go up here, back to Hamid's question. It will give the information to you. So device execution space is CUDA. CUDA is the GPU parallelization that we have. And it runs the DEM simulation. As you can see, for like 50,000 particles, it's running quite fast because it's running on the GPU. If I go also for 100, 200, or 300,000 particles, since I have the capacity on my GPU to run quite similar fast. So maybe not as fast, but quite similar fast, as fast as this one. Good. As soon as this part is done, if I go back to my folders, you see it's saving the data for us in like 0.05 second intervals. That's what the setting that we had on the DEM side. Let's wait for the DEM side to finish. Yes. Then I have this 0.25. So we have all the files which we need for the DEM simulation, but we also need to copy the files for the CFD part in there and for the coupling. So, and that's the next step here. Basically, we are copying them from this fluid field folder. Let's copy them to here. Yes, you can see the P, U, and alpha got copied here. And now basically we are ready to run the coupling simulation or CFD-DEM simulation using the Unresolved sphere PF+. So for the DEM part, again, I have the CUDA parallelization or the GPU parallelization. On the CFD, I'm running it on a single core on a serial approach because the CFD mesh is rather a small mesh, so it's not such a big mesh.
Okay, Bahram, I want to extend this session for 10 minutes because we don't have enough time for the questions and for the rest of the simulation.
So in this case, you are the master of the session. So then I will follow your lead, and that also relieves me. Thank you for doing that. Good. So this will take some time. I think that was one of the first questions that Hamid asked at the very beginning. How long does it take? Based on my experience, it will take over 1 hour, so around 1 hour 20 minutes to have 10 seconds of simulation. That's why I executed it in advance. So if I go back there, that's why I have it here. This is the finished simulation that I ran in advance. So I will stop that one. But you could see how fast it is. So we already have like 0.36 seconds of simulation. Good. I have done it in the past or earlier, and the last step which is listed here is conversion of the files or conversion of the data to VTK, the DEM data to VTK, that we be able to visualize them. I have also done that one, so we do it for the time between 0.25 seconds and 10. Why we are not doing it from time 0? Because we want to skip this settling time. Of course, we can also do that. Then you will see the particles settle, and from there they get fluidized. But let's take it easy and just go for the CFD-DEM part, which is the topic for today's session. Then we can simply open or run the ParaView. I hope that it runs. Yeah, and we can load the files. What I can tell you, I need to go to the other case. What I can tell you is the VTK series that we have here is synchronized with the foam.foam. So for those of you who are not familiar with it, so foam.foam or anything.foam is the dummy file that we can read into ParaView to load OpenFOAM simulations into ParaView. So this VTK series from PhasicFlow and this foam.foam file are nicely synchronized. So just by opening these two, I have both CFD and DEM part of the simulation. So the CFD-DEM and loaded into the ParaView in a synchronized way. So good. This is the foam.foam. This is the CFD side or the CFD-DEM, the CFD coupling side of the story. Let me make it a solid color and make it a bit opaque that we can see through it. So this is the CFD, and these are the particles which are sitting in there. As Hamid already mentioned, in the last time when we are visualizing the particles or we have been importing the particles, it just shows the center of mass of the particles. The option that we have, we can also visualize the full particles, but I will do it in a later stage and I will tell you why. At the moment, let's leave with the center of mass of the particles. And since our particles are small and we have too many of them, I think we can also do some visualization here. So let's color the particles by their velocity. So as you can see at the beginning, they have a velocity of almost 0. And if I run the post-processing, you can see the gas is coming in from the bottom and it's fluidizing the particles. What I can do, let's stop this one. Let's create a cut plane here and show the
Alpha.
Fluid velocity on alpha. Yeah, alpha is also nice. Let's go for Hamid's suggestion first. And you can, let's give it also a different color scheme that is better visible. Let's go for this one. Close. Good. You can already see where the particles exist. So let me turn off the particles for a second. Where the particle exists, the alpha is 0. Because there is no fluid or close to no fluid. And when there is no particles, or basically where there exists bubbles or air phase, you see it more red. So let's run the simulation, or let's run the post-processing with both together. So you can see how nicely where there is particles, we don't have fluid, and vice versa. Let me hide the particles and you see just the fluid behavior in there. Good. That's how you can do it with the center of mass of the particles. But as I said, you have also the possibility to visualize the full particles. For that one, you can use the glyph filter in there, and you need to use the sphere option in there. Good for scaling array. We use their diameter and use a scaling value of 1, and we want all the particles to be visualized using this glyph. If I visualize it, and you see it takes some time. So now you see them as real particles, so as really filled particles. And that's exactly the reason it took a bit time, and that's exactly the reason that why I did not do it for the video visualization, because if I want to run the video now, you see the rendering of each frame takes quite some time, so we could not see this fluent or this quite nice video thing in there. So we can see it takes some time.
Okay,
Good.
thank you,
Hamid.
Bahram. We have a few questions from my side from the chat. I think that we can dedicate the rest of the session to the questions. First question from the chat: in which file should we set the force threshold needed to keep the two particles together as one part? I mean, after passing threshold, two particles will separate from each other. I think that it happens automatically based on the dynamic forces that are acting on particles. If they want to stay together, they will stay. Otherwise, they will be separated based on the forces that are acting on each particle. And the next question from my side is that OpenFOAM is a parallel code using MPI, and PhasicFlow is a parallel code using OpenMP or CUDA. Is it possible to run both of them in parallel, and how is it possible?
That's a very good question. Yes, we can. We just simply. So in my case, I have the DEM side on CUDA parallel, so I don't need to do anything special in there. For the CFD side, as you said, we have the MPI parallelization, so I just go for the typical OpenFOAM procedure by using a decomposed part. So basically breaking my CFD domain and my CFD-DEM coupling domain into, in this case, two processors, and then running the command
decompose. Have you done the decompose?
Yes, I already did it. And like this. Then now my simulation is running on two cores for the CFD and for the part of the coupling, and is running on the GPU for the DEM part of the story. And as you could see, it got already quite faster.
Yeah, and what do you recommend when do we have to use parallelization in the CFD side? Do you have any recommendation?
Basically, yes. Thank you. That's a very good question. Basically, we can follow the same trend as we do on the CFD. So whenever we have cells more than 50 or 100,000 cells, we need to go for, or we should go for parallelization for a simple typical CFD case. If you have reactions or some specific things in there, then that's a different story. So better to say, try to decompose your case in a way that you have less than 100,000 or less than 50,000 cells per CPU core, and the number of CPU cores should not go above 70 or 80% of physical cores that you have on your machine. So if you have 16 cores, just parallelize up to 12 or maximum 14 cores.
And the other question is that in this lecture series, we covered DEM and CFD-DEM, but we didn't cover anything about the OpenFOAM. And what do you suggest for further reading for those who are interested in learning OpenFOAM?
Thank you. That's a very good question, and I would say that's a quite also relevant one for those of you who are also interested in OpenFOAM, into do the simulations and case setups in OpenFOAM. Our new lecture series, or the next series of our lecture series, Introduction to OpenFOAM, will start in roughly 2 weeks. Please stay tuned. We will announce it through our LinkedIn. So I think the announcement will come out somewhere during next week.
Thank you. And we have another question from the chat. It is reporting an error when he's executing sphere gram flow. From the error message, I see that he didn't follow the instruction in the outrun. So if you want to somehow resolve the problem, just follow the instructions in the outrun, execute the commands there one by one, then I think that you will solve your problem. Sorry, but I
Yes.
didn't explain the question because it's a long question and I just answered it myself.
Okay, thank you very much. So, and I think that's also a very good point, probably as a last point to close this session. I already mentioned it, these all-around files are usually a very nice reference and a helpful for me also personally. Please try to look through them and try to run the steps after each other. So there is usually a logic. As I said, for example, for the particle positioning and geometry creation, you can change it, but for running the CFD-DEM solver, you cannot do it without doing the DM preparations in advance or the mesh creation in advance.
Yes, and if you have any problems with the simulations and everything that is related to the PhasicFlow or PhasicFlowPlus, just feel free to create an issue in the repository and we will get back to you as soon as possible. Okay,
Great.
Bahram,
Thank you very much.
we are finished with the questions and I think that we can close this session here now.
Yes, as the closing word, so I have been already running the simulation in parallel mode also for the CFD side. As you can see, it's much faster just in this short time that we were talking. It reached almost 1 second of simulation. And now we have the two processor 0 and processor 1 folders in there. To know how to handle this, we simply do a reconstruct part and that put the mesh and all the simulations together and put it back to our root, to the simulation root folder. But for that one, and to get more information there, stay with us with our Open Forum lecture series. Thanks for being with us. In the next session, we will go into the Resolved CFD-DEM and looking forward to see you there. Have a nice day. Bye.
Okay, thank you, Bahram, for your nice cooperation and bye from me. See you next week.